I suggest we will follow our program, so we will go step by step during our papers according to our program, and I hope we will have time for coffee break, and the next session will be scheduled as a program. As I know, we have the only changes. It is about the paper contextual concept, meaning alignment based on prototype theory. We suggest to present it in this session if you are not against. And also, I suggest to have 15 time slot for each presentation. It means we have up to 10 minutes for your presentation and about 5 minutes to discussion session. So I invited the first paper is titled Mathematical Modeling to Evaluate the Accuracy of Computer Vision for the Near-Zero Motion Detection of Astronomical Objects.
Hi all, do you see my screen?
Yeah.
Okay, so good afternoon, dear participants of the conference. Today, the authors from Kharkiv National University of Radio Electronics, Ukraine, present the paper called Mathematical Modeling to Evaluate the Accuracy of Computer Vision for the Near-Zero Motion Detection for Astronomical Objects. The computer vision technology in all mobile applications and desktop software for the astronomical video or series of CCD images processing is designed to detect and recognize objects with the different apparent motion: zero motion, fixed object, near zero motion, normal motion, and high speed motion. There is no one modern unified algorithm that can detect and recognize all objects with motion in all described above case. In our research, we focused on the detection algorithms for the objects with a near zero motion. So, what is the object which has the near zero apparent motion? This is the kind of object which has a very small shift in pixels between frames, and this shift is commensurate with the measuring error of its position. Such an object has a motion between images in series that is less than or equal to 3 root mean square RMS errors of its position's measurement. There are a lot of types of moving objects that have a near zero apparent motion. All of them belongs to robots, drones, satellites, rockets, comets, asteroids, and even bullets. There are different observational conditions for the near zero apparent motion. Object direction, which is perpendicular to the shooting point, very short exposure time, very big distance to the object, or extremely slow apparent motion of the investigated object during its movement. Almost all encapsulated detection algorithms related to the near-zero apparent motion are based on verification of the following hypothesis: H0, that the object has no apparent motion in both directions, x and y, and alternative hypothesis H1, that the object has at least 3 RMS velocity or more. In this research, we presented the few most popular detection algorithms for the near-zero apparent motion, implemented on both the maximum likelihood criterion and the Fisher F criterion. The common detection principle is to use the quality indicators of the object's detection, like conditional probability of false detection and the conditional probability of true detection. The hypotheses are often tested using the maximum likelihood criterion or another criterion from the Bayesian group. The final statistical value for such criteria is a likelihood ratio, which is simulated with the critical value. We selected the situation when the variance of object's position is known from the preliminary observations and calculations. So the general view of the substitutional method based on the maximum likelihood criterion for the near-zero apparent motion detection of objects with known variance is presented in this slide. If some parameters of a likelihood function are unknown and there is no possibility to predefine the critical values of decision statistics, it's recommended to use the detection algorithm implemented on the Fisher-F criterion. Using F-test, it's possible to verify statistical significance of the velocity of an object along both coordinates. More major advantages are that the F distribution has no dependency on distribution of the positional errors and has values of the Fisher distribution statistics, which are tabulated. The general view of the method based on the Fisher-F criterion, which checks the statistical significance of the velocity of an object along both coordinates x and y, is presented in this slide. You can find the detailed information about the developed described methods by authors in the few important publications in the international journals with impact factor 5+. To provide the evidence of a high-quality detection of the near-zero apparent motion of objects, a computer vision technology with encapsulated detection algorithms should be tested not only in the real situation with the online input data streams, but also in the virtual simulation using the predefined dataset. Such a dataset can be immediately created as well as the in situ data from the real series of images. On this slide, you can see the very brief scheme of the realization of statistical modeling. So we have the model of apparent motion, add the random deviations, apply the detected methods, and calculate the quality indicators. But for the in situ modeling, the brief scheme of realization is different. We have the real series of images from the telescope, then find all fixed objects in these images and create a set of such objects, like internal catalog of fixed objects. After this, we get the deviations of the positional estimates and calculate the deterministic values of the object's movement. Then again, applying the detected methods and calculate the indicators of quality. On this slide, you can see preconditions and constants for the mathematical modeling we used in our research. For example, number of objects for Sun telescope was more than 100,000 objects, and for Genon telescope, more than 500,000 of objects. There are for randomization values distributed by the normal law. We used the ziggurat method as a more accurate method for randomization. The more detailed UML diagram of the mathematical modeling is presented on this slide. We perform, first of all, modeling of hypothesis H0 when the object has no apparent motion, and then modeling of the alternative hypothesis H1, which has at least 3 RMS apparent motion. Then determine critical values, compare them, and count the exceedance of critical values. All this data allow us to determine the conditional probability of true detection. On this slide, you can see the full UML diagram of the one case experiment of mathematical modeling. As you can see, we have a model of apparent motion, linear OLS least square evaluation of motion parameters, then determination of the residual sums of square deviations, again, different types of likelihood ratio estimation, and separate estimation of Fisher-F criterion using already calculated residual sums of square deviations. Based on the conditional probability of true detection of the near-zero apparent motion of an object, the detection curves for the investigated detection algorithms were created as a proof of efficiency of them. On the following slides, you can see the detection curves for the substitutional method based on maximum likelihood criterion, dotted line, and the method based on Fisher-F criterion, solid line, based on statistical and in situ modeling. The analysis showed that the substitutional method based on a maximum likelihood criterion is not effective enough when the motion velocity is less than 3 RMS. So the common approach using the maximum likelihood criterion methods is good enough for the normal apparent motion, but not for near zero apparent motion. While the method based on the Fisher-F criterion is more delicate to changes of the motion of an object. So even if we have 0.5 RMS speed, Fisher-F criterion can have a possibility to detect such object, even with the small conditional probability of true detection, but anyway it can. But method with maximum likelihood criterion does not at all for this. Thank you for your attention.
Thank you very much. Any questions, please, dear participants? Do you have any questions? I'd like to clarify the one issue. As I understand, you check your approach the only on artificial data. And how you evaluate your method, your model, how it would be if you apply to the real data?
We had two types of modeling: statistical, as artificial you mentioned, and in situ modeling. And as I mentioned on this slide, we used real data from 2 telescopes. This is information regarding these telescopes and their characteristics with different types of CCD camera, pixel size, and different exposure time. We made observations to have different observational conditions to observe near zero motion objects in series of images. And as I mentioned here, you can see number of objects from different type of telescopes that we use. So we received a lot of series of images, and for example, pick from them 500,000 objects of these images, real images of objects.
Okay, thank you. Anybody has any questions? Please don't hesitate. Okay, thank you very much for your presentation. We need to follow our program, and I invited the authors to present the next paper, improving accuracy by ensuring invariance of two-dimensional binary images in intelligent systems. It seems like we don't have authors to present this paper. So we can go to the next. Yes, please.
Hello, just a moment, some technical information that in Kharkiv there are some troubles with electricity, I know, in some regions, maybe, so maybe it is possible that authors cannot join us.
Maybe they can join us later, and we can a little bit reschedule.
If it's possible, I could give my talk. My name is Peter Kogut.
If the other participants not against, because I suggest to follow the program.
Yep, maybe we can go one by one and skip the one that is missing and proceed with next papers.
So if you are not against, we go to the next paper. It is programming the formation of different scalar models for lossless image compression.
Yep, just a moment. I'm sharing my screen.
Welcome.
Can you see my screen? Can you hear me well?
We can hear you.
Yeah, we see
Okay.
Can see you.
It's my second time presenting the paper when the previous candidate is missing and I need to go faster. Okay. Okay. Just a moment. Okay, let me start our presentation. Good morning, dear colleagues. Today we're presenting you a result of the research of the topic, programming the formation of different color models for lossless image compression. In the study, we propose a method and corresponding algorithm for selecting adaptive difference color models with integer coefficients for improving the efficiency of progressive lossless image compression. To speed up the output of large images in compression formats with losses, graphic formats that use progressive hierarchical pixel processing have already been developed. This approach allows us to stop recording after the compression of the layer with a number of pixels not less than the output area on each axis without waiting for the reproduction of all the pixels of the image. Encoding pixels of images in common graphic formats that perform lossless compression in the most often performed sequentially in lines from top to bottom and in each line in the row from left to right. Therefore, it's possible to display a compressed image in these formats only after decoding of all the pixels. The goal of the research is developing the HBFLC format for progressive hierarchical lossless image compression, which will allow quickly obtaining reduced copies of the image without decoding the entire file. In this article, we propose a method and a corresponding algorithm for increased code redundancy for reducing inter-element redundancy using adaptive difference color models with integer coefficients in the process of such compression. Any data compression is possible due to reduction of elimination of redundancies. Three main types of redundancies are distinguished in images. Visual, consisting in the presence of information that is not perceived by the human visual system. Inter-element or spatial, manifested in the correlation of brightnesses of adjacent pixels. And coded, revealed when using codes of the same length of elements with different probabilities. It's common knowledge that the more types of redundancies of each type are processed by the graphic format, the more effective the compression is. But in the process of lossless compression, information is not lost. That's why the first type of redundancy is not reduced. Therefore, lossless image compression in archivers and graphic formats must often contain four main stages. First stage, compression by context-dependent algorithm. Then the transition to an alternative color model, then usage of predictors, and after that, compression by a context-independent algorithm. It's extremely important to remember the basic principle of context-independent coding. Elements with a higher probability should be encoded with sequence of bits for shorter lengths than the code length of elements with a lower probability. According to the fundamental position of informational theory, to minimize the length of the sequence code, the element brightness with the probability of p should be encoded with a logarithm of p to the base of 2 bits. Therefore, the average code length of the block element after the application of any context-independent algorithm, according to Shannon's formula, cannot be less than the entropy of the source. As a result, the entropy of the source decreases with the increase in non-uniformity of the distribution of probabilities between the elements. And our main goal is to increase the non-uniformity of the frequencies using different color models with integer coefficients. As an alternative to sequential pixel traversal, we propose a progressive hierarchical traversal by which, on the first layer, we must consistently bypass pixels of the image, beginning with the first on lines from top to bottom, and in each line in a row from left to right, with a step of 2 power of k, when k is determined from the condition that you can see on the screen. On the next layers, from 2 to k+1, intermediate pixels of the image are processed in 2 passes. On the first pass, those of them which are contained on crossing of diagonals of squares with vertices in adjacent pixels of the previous layer, and in the second pass, unprocessed pixels are processed between adjacent pixels of the previous layer and the first pass with the same step on columns and with twice reduced on lines. Schematically, the sequence of hierarchical traversal is shown in this diagram. Different color models are predictors used to reduce entropy. The fact is that firstly, the color of pixels in the three-component color model can be represented in the form of coordinates by three linearly independent vectors of any basic colors. Secondly, different image components display sufficiently similar geometrical spatial structure objects. An example of such similarity you can clearly see on the screen. Different color models are used to maximize entropy reduction due to their intercomponent decorrelation. Therefore, they increase the efficiency of the application of the context-independent algorithm, although they don't directly perform that data compression. For an ambitious decoding, there can be a maximum of 2 differences in the difference color model. The correlation coefficients between pairs of components in the RGB color model for different images can differ significantly from each other, and one of the components of such arbitrary pair with a strong correlation can be replaced by the difference with another component. If this will reduce the entropy in the further process of context-independent coding. Using component differences instead of components luminance of the RGB color model performs intercomponent decorrelation, just as predictors implement decorrelation between adjacent pixel luminances. When calculating the differences in the luminance of the components in cases where the luminance values of the subtractor insignificantly exceed the luminance values of the reduced one, negative values of the difference are obtained, which when stored in unsigned 8-bit components of the color model are transformed into values close to 256 due to overflow. And when the luminance values of the subtractor are slightly smaller than the luminance values of the reduced one, values close to 0 are obtained in differences. This dispersion of color models values negatively affects the accuracy of prediction and therefore increases entropy. To avoid such dispersion of the values of the differences of close luminances, it's customary to shift them to the middle of the range of possible component values, as is done in YCBCR color model. In the individual component in the image, I'm sorry. If the individual components in the image were coded into separate compressed blocks, then the length of the entropy code of the difference of components would be equal to the length of the entropy code of the opposite difference, and the following 16 color models would be alternative. Among these color models of each image, we choose the one that provides the lowest entropy. But the luminances of the pixel components are stored consistently, and therefore the length of the entropy code of the difference of the components is not equal to the length of the entropy code of the opposite difference. As a result, the number of alternative differential color models increases from 16 to 49. All of them you can see on the screen. If we analyze the effectiveness of differential color models with the same reducibles or minuses, then their number will be reduced from 49 to 31. We will present the result of testing of our proposed difference color model selection algorithm for each image on the test set AST. This set contains both photorealistic and discrete tone images. To ensure that tests are conducted correctly, you can check the main characteristics of these images of this set. As you can see, different color models provide the lowest entropy for different images. We can see that on average for this set, due to the use of different color models with integer coefficients, the compression ratio is decreased by 0.36. Moreover, about 90% of this decrease occurred due to the shift of the median difference to the middle of the range of the possible values. The effectiveness of different color models differs first of all for different types of images. If for photorealistic images, the compression ratio is decreased by an average of 0.98, then for discrete tone images only by 0.01, since they have a low level of correlation between components. For image number 1, there was even a fallback to the RGB color model, as an alternative difference color models reduced the predicted entropy code by less than 1%. The choice of different color models, not from the 49, but from 31, with the same amino acids or substrates, forms models with opposite components in 25% of the images, which significantly increases their compression ratio. On the other hand, this doesn't lead to a drastic acceleration of compression, because most of the time in the process of choosing different color models is spent on forming a command frequency and their differences. In general, the use of different color models significantly, on average by more than 13% according to table 2, slows down encoding, not only due to the need to choose such a model from among alternatives, but also due to the orientation to a context-independent algorithm that encodes individual literals. However, the time of the image decoding due to the use of these color models is increased by only a tenth of a second, which together with a significant reduction in the coefficient ratio makes it possible to use them effectively in practice. The conclusions of the research are the following. It's possible to reduce the compression ratio of the images in 3-component color models, not only due to the data decorrelation of individual components, but also with the help of intercomponent decorrelation by switching to different color models. Intercomponent decorrelation should be performed in such a way to enhance the properties of the image used by the algorithm, presenting a direct compression of the selected graphic format. For example, to minimize the predicted length of the entropy code. The use of the different color models with integer coefficients in the process of progressive hierarchical compression of lossless images makes it possible to reduce the compression ratio of photorealistic images by an average of 0.98. To ensure the smallest coefficient ratio, a different color models with integer coefficients should be chosen from all 49 alternatives. In order to increase the efficiency of the application of different color models with integer difference coefficients, the median differences of the basic components RG and B should be shifted into the middle of the range of possible values. Integer difference color models provide significant improvements in the lossless compression efficiency of 3-component photorealistic images in formats that use predictors and may therefore be implemented in future standards level versions of such formats. In the future, we'll aim with the aim of further reducing the file sizes of lossless compressed images in the process of progressive hierarchical traversal and speeding up decoding. We plan to increase the efficiency of using symmetric and asymmetric predictors by applying different color models with integer coefficients to image fragments. We are working on an algorithm for dividing images into large rectangular pieces with different adaptive difference color models by analyzing their median differences. Thank you for your attention.
Thank you very much for your presentation. Do you have any questions? Could you please explain in more detail maybe how we can apply the results of your research in practice? So as I understand, you make some testing, the method on some images, and how we can apply the results you obtain.
To the real life, you mean? Exactly. So ideally, when the research is done and the result of this research will be new format of the image that will allow you to compress the images with the most compression ratio that is possible, that we can in the end reach. So the result of the research will be the new image format, the same as we have, for example, JPEG, PNG, the same image format will be developed here. And of course, we need to find like the ways to increase this compression ratio. And here is one of the steps that was done to do that, to achieve that.
So you think that in future it would be like an application that everybody can use, or
yes,
how
sure.
you plan?
So, you know, even for example, in Telegram or even iPhone has its own image format. And of course, this image format was developed to, of course, to save the image, the file, the photo in the most efficient way. So the result of our research is how to make the compression rate so that the image will take less space to be saved. But when the user opens the image, still everything. So we are now working on lossless image compression, which means that we can't afford any information, any pixel of the image to just disappear. So we need to ensure that when the image is opened, all the pixels are the same as they were before.
Okay, thank you. Anybody else? Any questions? Okay, thank you very much for your presentation and
Thank you.
And let's move on the next paper. It is face detection for video surveillance-based security system.
Yes. Hi.
Okay.
I hope my screen is visible. Is it? Can you
Veronica,
see it?
please
Just a
stop.
moment. I can't close my window because I'm. Yep. Maybe you can share and it will close mine. Maybe you can try.
Yes. Now I'm sharing it.
I'm
And,
not sure that other people
okay.
can share at the same time.
Just a moment.
Just stop sharing.
Yep, I know, but I have.
Button stop
I'm
sharing.
just a moment. I need to find this button. I'm a bit confused. Was oh no, it wasn't.
It is usually on
Goodness.
the top or in the bottom of the screen.
Yeah, but I can't find the screen. Just
Like
you see.
separated window.
Yep.
No.
Sorry. Just a Zoom screen just disappeared, and okay, I'll do the following. I'll just close it, and that's it. Sorry, I'm so sorry.
Maybe
Just a
your
moment.
Zoom screen is
Because I have.
oh,
Yep,
yeah,
now it's.
Everything is okay. Yeah.
Yes.
So welcome with your presentation.
Is my screen visible?
Yeah.
Okay. Let's start. Hello, dear conference participants. The topic of my report is face detection for video surveillance-based security system. To date, great progress has been made in computer vision tasks, including the task of face detection, but the diversity of detection methods creates the problem of choosing the most appropriate to solve real world problems, where there are specific requirements for accuracy, time, and condition in which this method will work. The face recognition task itself consists of several parts. These are face detection, face alignment, feature extraction, and finally the classification. But the main focus of this work is detection, and the aim is to find the most appropriate method that will satisfy the requirements. And the purpose of this work is presented in more detail on this slide, along with the object and subject matter of the study. Also, we additionally put restrictions on the recognition system itself, which will use our chosen method in the first stage. Here they are. So we chose the following methods for testing due to the publication rating. You can see them on the current slide. In these publications, it wasn't specified how the quality of the methods depends on the parameters of the geometrical transformations of the faces to be fed to the input, and the frame processing time was also measured on the different equipment and they cannot be compared. And as summary of the date of appearance of the methods, the accuracy and the presence of landmarks of the face which the method can additionally provide is given in table 1. So the following experiments were chosen by which the detectors were compared. These are the dependence of detection quality on face rotation, the size of the face, and the processing speed of a single frame at VGA and HD resolutions. In the experiments, we used general models from publicly available repositories. For the first experiment, a synthetic dataset was created using Blender software, in which the face was translated into a 3D object and rendered with a rotation of 1 degree from -90 to +90 degrees. And a left motion plot of the different methods is shown in figure 2. Below, the methods were additionally ranked from left to right, from less to more accurate. And the same is true for up-down motion. In this case, face boxes, retina, face, and DSFD show the same results. Next, an experiment was conducted to test the dependence of detection quality on face size. For this purpose, synthetic images were created with faces ranging in size from 20 to 310 pixels. And these images were fed to the detectors, and an example of one result of the processing is shown on this slide. Based on the result of these experiments, a plot was made in figure 5, and also the detectors were ranked. Next, the detectors were compared in terms of processing speed per frame. The density of the frame processing time distribution for VGA resolution images is shown in figure 6. The same results were obtained for HD resolution images. The conclusions of the time comparison are presented on the current slide. The methods are ranked from slow to fast, from left to right. So to choose the most suitable method, it was decided to compare the parameters of the methods and the results obtained according to the following criteria. average precision, presence of landmarks, the maximum range of rotation angle for which the method detects faces with confidence of more than 90%. The minimum face size that can be detected with a confidence of more than 90%, and finally the minimum time to process one frame for VGA images. And based off these parameters, the methods obtain the following values. See figure 8. And based off this values, the retina phase mobile net method was selected. The work of the selected detection methods was used in the recognition system that consisted of the following components. And this slide shows an example of real world images from which the testing dataset was created to measure the quality of recognition. So the system was tested on common metrics on previous dataset. Please see figure 10, and the AUC stroke value at the optimal threshold is shown below. As system architecture, technology, and detailed interaction of system components are shown on this slide. And a small illustration of how the system works. This video shows how the system recognizes a person and shows notifications about it in the user interface. And finally, let's come up with some conclusions. The custom datasets have been collected for testing the following models on the robustness to face rotation, phase resizing, and time cost. The system has also been tested for accuracy using the AUC ROC on its dataset under the real world conditions. And the best models in terms of rotation for array interface ResNet, DSFD, and array interface mobile net. For phase sizes, the best results were shown by MTC-NN, DSFD, array interface ResNet models, and the detection time measurements showed that the fastest array interface mobile net and phase boxes. In the future, conducting additional research on other stages of phase recognition would be advisable. Thank you for your attention.
Thank you very much for your presentation. Anybody has any questions?
Yes, I have one question.
Yes, please.
mentioned a set of methods for face recognition. And how do you think, how to evaluate these methods and choose particular one for face recognition?
Sorry, I mentioned only face detection methods, but if we are talking about face recognition, it's here on this slide that sometimes after feature extraction we have classification stage, and here in previous I think 2 years we have a lot of evolution of this methods, and it's a topic of another research, but for your question, it could be even SVM or some tree forest, or some of SAM's neural networks that will compare two feature vectors of faces. I hope I will answer.
Okay, thank you.
Satisfied? Anybody else? Okay, I have a quite short question.
Yes,
Your concern to security system, how do you apply your results to security system, or what do you mean when you talk about security system?
Security system, like I showed this video, is a common system that consists of user interface and UI for it, and it's a system to help security guard to, for example, protect office, and quad will receive notifications if some person will come to area, and will take its own decision of action that guard will do. Is
As I
it
understand
clear?
correctly, you mean that this system should react whether the person who detected is not the recognized or something like this? Or?
Yes, correct.
Okay, thank you. Thank you very much.
Thank you.
Nobody wants to continue. Okay, so we move on to the next paper. It is Sentinel-2 and Modis data fusion for generation of daily cloud-free images at the sentinel resolution level. Please welcome.
Hello, everybody. Can you see my screen?
Yes.
Okay, great. My name is Peter Kogut, and today I would like to share with you some our recent results that we obtained in cooperation with Nataliia and Petro Martinyuk. Before I will characterize the main object of our consideration, I would like to say a few words about the remote sensing technique, especially in agriculture. I guess you are well informed that over the past few decades, the remote sensing has been increasingly contributing to many agricultural monitoring services, by providing worldwide systematic observation data concerning the current state of the crop conditions in order to give early insight into how well the crops are doing and if they are needing water or nutrients. Typically, to provide useful information of the crop status, it is important to monitor the selected fields on a regular basis. How can we do it? By car, by horse, by foot? No, the unique normal way for this is the Earth observation using a number of satellites located at different orbits and equipped by special optical systems. As a result, we can receive with some periodicity a collection of optical images of those territories which are the focus of our interest. Well, when we speak about satellite image, we usually understand it as follows. We have a rectangle domain omega. Basically, it is one of our interests, and we associate with this domain some vector valued mapping where each component of this mapping stands for the reflectance of the given territory in the corresponding electromagnetic spectrum or band. In order to characterize the main object of our consideration in this talk, I would like to know that a very serious obstacle to utilization of optical remote sensing satellite images is a risk of cloud and cloud shadow distortion issues. Over 50% of all satellite images of Earth's surface are covered by clouds or they are cloud contaminated globally. For illustration, let us bring a look at this slide. You can see here a cloud corrupted satellite multi-band image of some territories that has been delivered from Sentinel-2 satellite in July last year. As you see, the measure of degradation of this image is such that we cannot rely even on the brightness inside of the damaged region. As a result, some subdomain of such images becomes absolutely invisible, and therefore we face with the risk of missing information in optical remote sensing data. Let me pass to the formal statement of our problem. Properly speaking, we have two sample grids, where one of them corresponds to the high resolution, whereas the second one to the low resolution. We also have a collection of multispectral images of some territory S1, S2, and so on from Sentinel that were taken at time instance T1, T2, and so on. We assume that these images are in good resolution. So we also have a collection of region D1, D2, where the corresponding Sentinel imagery are covered by clouds. In addition, we suppose that we have a modest image of the same territory. We denote this image by capital M, and this image has been captured at the some time Tm. In order to give a precise statement of the problem, we assume that you can see some of our assumptions that we introduce. And the main problem is how to generate a new synthetic daily multi-band image of the same territory from the day Tm at the Sentinel-2 special resolution level, utilizing for that the above mentioned data. We begin with some preliminaries. In accordance with mathematical morphology doctrine, the reliable information in every image is contained in the level sets. In practice, in order to characterize the level set for a given image, it's enough to compute the ratio gradient over its norm for some small value t, where capital U stands for the solution of indicated initial boundary value problem with one d Laplace operator in principal part. The second important characteristic of images, it is the so-called texture index. We introduce it as follows. You can see this red line, where G is a given edge-stopping function, and the expression G star V stands determines the convolution of two functions. For our further analysis, we need to introduce the following characteristic. We say that multi-band images, as with the hat, a structural prototype for the corresponding cloud corrupted images from Sentinel if they are defined by the rule 7. In fact, the structural prototype substitutes the damage zone in the current image by the same part from the previous image. As a result, we have a sequence of images without any combination. Before we give a precise statement of the problem, we know that the crucial point in each statement is the time instance where the modis image has been captured, I mean TM. So we can distinguish three possible cases. The first case, the modis image was captured together with some, in the same time with some sentinel. The second case, modis image was captured between two sentinels, and the last one, the modis was captured after the last sentinel image. As a result, we will distinguish three different statements of the data fusion problem. The first problem, we call it as restoration problem. This problem consists in restoration of the damaged sentinel image using the result of its fusion with the cloud-free modis image. The second problem we call interpolation problem. This problem consists in generation of new optical image at the sentinel level of spatial resolution using the result of the fusion of cloud-free modis image with a predicted structural prototype from the given day. And the extrapolation problem consists in generation of new image using the result of the data simulation from the cloud-free modis image into the structural prototype of the last sentinel image. In order to correctly define the intermediate structural prototype, we make use the model 8, 9, 10, where the right-hand side can be viewed as a distributed control with the state constraint in the form of 11. In fact, we deal in this case with a special optimal control problem for the parabolic equation 8. Unfortunately, I have no time in order to drill down into details of this challenging problem. So let me pass to the next slide. At this slide, we give a precise statement of the restoration problem. We say that multiband image S, capital S, is a solution of restoration problem if it is given by the rule, you can see this at the top of the slide, where U sub 0 is a solution of the following constrained minimization problem. We know that the other problems, I mean interpolation problem and the extrapolation problem, they can be stated in a similar manner. It is worth to notice that above-mentioned variational problem is well defined, and using the direct method of calculus of variation, we can prove the following results. Theorem 1 says that this problem admits at least one solution, whereas in theorem 2, we give some optimality conditions which we utilize in our numerical simulation. We are now in a position to look at the results of numerical simulation. In order to illustrate the proposed approach for the restoration of satellite multispectral images, we have used two sentinel images over the Dnipro airport area. One of them has been captured in July 15, the second one in July 17. We see that the significant part of the second image is damaged by a cloud. At this slide, we have a cloud-free modis image from the 1st July. This image, as you see, in a poor resolution. Since the modis image has been captured between two sentinel images, we solve the interpolation problem A2. I don't want, as I said before, go into detail of this problem. So the results of such interpolation you can see at this slide. As for the validation of the obtained results, these issues are described in all details in our forthcoming paper. So thank you for your attention.
Thank you very much for your presentation. Anybody wants to start the discussion? Do you have any questions? Okay, I'd like just clarify how we can use your result in others' application, how it can be useful for others, how you can explain it, what you recommend to use from your results.
You know, there are many companies and corporations they used satellite images for some prediction of status of crop fields and so on. So if we take, for instance, such corporation as Sphere, for instance, Yeo's data, they use exactly our approach in their current work. So I don't see any problem in this context.
So you think it can be commercial purposes to
Yes. I don't want to open all details of this approach, as you understand. So, but anyway, this product is absolutely applicable for practical problems.
Okay, thank you very much.
Thank you.
Thank you for participation. And now I'd like to invite the paper contextual concept meaning alignment based on prototype theory. It is a little bit changes in our schedule, and we invited authors.
Okay, good afternoon, dear colleagues. Today I would like to show you the results of our research titled Contextual Concept Meaning Alignment based on prototype theory. The introduction of autonomous intelligent agents promises to increase the productivity in various areas of the economy. The autonomous agents are capable of intentional functioning in the natural environment, gathering, assessing information, making decisions, and learning using feedbacks. They use their own conceptualization of the world, which they are developing constantly in the process of learning, not unlike humans do. However, when we compare the capabilities of current agents with the capabilities of humans, we see that traditional ontological approach used to build those conceptualizations much lacking in the department of richness, fuzziness, context dependency in the meaning of context. In our research, we take the insights from the human cognitive theory, from cognitive linguistics, in order to improve the capabilities of intelligent agents and making parallels between the two. For cognitive linguistics suggests that human representation concept is vague and fuzzy and have multiple meanings possible for any concept. It is also represents the properties of being generic, especially when context is not provided, and opaque. That is, there's no clear rules showing why such object belong to such category. There are two basic principles of cognitive linguistics: non-modularism principle, saying that language is not only as a result product of all cognitive abilities of a person, and non-objectivist principle, saying that the meaning of concept is always or human always in using his biases, his knowledge, his values to build the understanding of such context. Intelligent agents in this area are very similar to human because they also take information from multiple sources, from their database, from other agents, and from reasoning, and from feedbacks. And they also have local conceptualizations which are specific to such agents. Current theories of concepts have difficulties to model such properties of natural human conceptualization, such as fluency, context dependency, being able to combine context several, or being able to build new meanings of concept. Current knowledge models for intelligent agents are based on ontologies, and current research in the area of ontologies highlights the shared conceptualization. That is, the meaning of concept are represented as taxonomy, which when specific concepts have immutable, fixed meanings defined by their properties. However, in natural environment, the meaning of concept is not only subjective, but is for every intelligent agent, but also it is evolving with time, with experience, and always is contextual. Research, however, in recent time, the research started gaining traction about so-called local agent-specific ontologies and ontological networks, when different meanings of context are linked by mappings or bridge. Our research assumptions say that each intelligent creates and uses a conceptualization of the words, and it's constantly updated. This conceptualization is a process of learning, and this as a consequence, the agent's local ontology is dynamic and unique to this agent. Agent knowledge is tested for consistency and is updated in the process of resolving practical tasks. The central part of cognitive linguistics is a prototype theory, which says that the meaning of concept is defined by a set of real-world projects which work as prototypes, which is representative of meaning of such context. And we use this approach to update or to introduce the conceptual meaning of context. In our research, we model the meaning of concept as a separate ontology. In the root, we have the root meaning, which provides the identity of meaning of this concept. So it is the common part of everything. And we can specialize nodes in this ontology, for example, default or generic meaning saying which is used when the context is not specified, or a reference meaning which is used in communication between different intelligent agents. In these ontologies, there is built using generalization, specialization relationships, but there are also mapping relationship allowing to project or move meanings from one interpretation of concept to another interpretation of concept, and they're also used in relationship, which creates the relationship with a specific context where such concept interpretation is used. We prefer to represent on model autonomous intelligent agents as a situational aware system or situation aware agent. Such agents constantly monitoring their environment, they making decisions and performing actions. And for such kind of systems, the primary activity is the identification and modeling of environment or context in which they are operating. And this model could be represented using concept from ontology. Therefore, the context or the model of environment for such system is the primary model, primary result. The information, in order to connect with the knowledge about situations, intelligent agents use the typical concepts, context which we will also propose to organize according to prototype theory. That is, we propose to add to semantic memory modeled by ontologies, the episodic memory modeled by this typical prototypical context. And when this prototypical context is identified, we can simply use or establish it or define the meaning or the interpretation of specific concept interpretation, which can be used in such and such situation, in such and such task or such and such context. Moreover, such approach allows us also to build new concept meanings, because as a first step, when this specific context is evaluated or identified, we usually compare this our current context model with existing models in the repository of prototypical context. And when such link is not established, we can build the new situation or even new meanings of such context. We think that this prototypical approach is or approach based on prototype theory presents a way to build or model multiple contextual meanings for each concept, provide the necessary fuzziness of concept meanings which are adapted to their usage. And also it is creates a way to model or create the new meanings for each intelligent agent in the process of learning. So thank you for your attention. I am waiting for your questions.
Thank you very much for your presentation. I'd like to ask you about agents. You mean that each agent will have the separate ontology? Do you estimate how many resources you need to update these ontologies to keep it and so on?
The estimate depends very much on the area where those and the task where those agents will work. Currently, we have the examples, for example, on autonomous driving, such a kind of agents, and currently they can be implemented even within a specific car. So current technologies allow to or have enough of resources to implement those systems.
Okay, thank you. It's interesting, really. Anybody has any questions? Okay, thank you very much for participating. And now we have the time for coffee break. And we are waiting for everybody for the next session in 15 minutes. Have a coffee break.